Very well. So our topic is second order differential equation, but before talking about how we are solving second order differential equations, how we classify them, we need some basic definitions. Remember that we start talking about initial value problem, and we talked about boundary value problem. For initial value problem, if you have the nth order differential equation, linear differential equation, it doesn't matter if it's homogeneous or non-homogeneous. Linear differential equation, like an x, the nth derivative of y, plus an minus 1 of x, the nth minus 1 derivative, plus the middle terms, a1x, y prime, plus a sub 0x, y equals to g of x. Then here we are dealing with this differential equation. If we are imposing some conditions, some constraints related to just one x value, like if we say, hey, y at x sub 0 is y sub 0. These are the conditions. Y prime at x sub 0 must be y1. And the rest of the conditions, we can impose as many conditions as we want, depending on the derivative and the order. N minus 1 at x sub 0 is y n minus 1. Then we call this guy an initial value problem. We try to solve this differential equation. But if you are imposing more than one x value, our conditions are related to more than x, we are dealing with boundary value problem. So we define an nth order linear differential equation, the same format, the same process, a and x, the nth derivative plus y prime, y equals to g of x, is called a boundary value problem. If you have, for example, y at x sub 0 equals to y sub 0, and also we have y at x sub 1 equals to y1. We talked about the uniqueness and existence of the solution. Remember that an cannot be equal to 0, and the rest of the coefficients, and also if you have a non-homogeneous differential equation, these must be continuous on an interval. Then the theorem guarantees that we can find a solution, and that solution is unique. Then we start talking about a linear operator. A linear operator. You're going to work with linear operators later in linear algebra as well. A linear operator is a function. Let us denote this function by L. This function is a function that preserves linearity. This function preserves linearity. What do we mean by that? So suppose you have the sum of two functions, L of f plus g. In linear algebra, we can just change this into two vectors, v and w. So linearity, it means that if we find the composition of L and f plus g, it is equal to L of f, the transformation that has on f plus the transformation on g. And also L of af becomes a L of f. It means that if you multiply your function, later on the scalar multiplication for the vectors a times b, you can write this a, the constant, outside L, outside this new transformation. So we say that, hey, the linear transformation preserves linearity. Now recall that when it comes to differential equations, we say that d, which we define as d dx, is an example of a linear operator. It's called differential operator. Remember that d of d or d of dx can be written as the differential of the differential, which is the second differential. And you can continue this process, d of d, and finally n times is d to the n, the nth differential. We also define, example, the nth order differential operator. The nth order differential operator. Very good. Or the nth order polynomial operator, which is defined this way. L is equal to an x dn, d to the n, plus an minus 1 x, these are just our coefficients, plus the middle terms, a1x d plus a sub 0 x. Let us take a look at one example. So our example says, use the differential operator to express your differential equation using d. So the given differential equation to us is the second derivative of y plus 5y prime plus 6y, which on the right hand side is equal to, this is a non-homogeneous differential equation, 5x minus 3. Very good. So recall that the differential operator is d dx. So take a look at this. Y prime is d dx of y, which is d of y. What about the second derivative? The second derivative is d dx of y, which is d squared of y. So far, so good. This guy becomes d squared of y plus 5 d of y plus 6. What is y? Well, when you're dealing with your y, it means that here you only have d to 0. Y is d to 0 of y. The zeroth derivative of the function is equal to the function itself. If I take the zeroth derivative, I'm putting that inside the parentheses to denote that I'm taking the zeroth derivative of the function. The first derivative, the second derivative, and the zeroth derivative. So plus 6y is equal to 5x minus 3. Okay, take a look at this. What I'm going to do, I'm going to factor out my y. Factor out. I get y d squared plus 5d plus 6 equals to 5x minus 3. So let us talk about linearly dependent